Okay, let's just get started because this is a topic I really love. Privacy mostly. Security is great as well, and we'll look into a lot of that, but I had to cut so much stuff because I love talking about this. Like even an hour wouldn't be enough, but don't worry, I cut it down. But we'll be going fast, and I give you a lot of little things to put. You don't have to remember everything, but I'm hoping to give you some things to bring back to wherever you work and to use in your professional life, or maybe just a refresher of some things you've forgotten, right? My name is Nikolai. First of all, I am a developer. I program every day. I'm a consultant, and I work at a firm here in Oslo called Variant. So I live and work here, so I'm a local speaker. The big thing in a talk like this that you always see is like, maybe the title should have been this, right? I'm not a lawyer, and I do not give legal advice. We'll be talking about some legal stuff, so now it's said. I've divided it up to kind of 4 topics to make it a bit easier to follow where we are and what I'm going to be talking about. So I'm going to start with the most fun part, which is kind of navigating the complexity of legal compliance. Wow, that's a mouthful, right? So we'll go into some like history and some laws, and if you're not from the European Economic Area, you're going to learn a lot, and you're going to start hating the area because it's a lot of rules and laws. But yeah, we've been handling a lot the last few years and still are. Then we'll move on to anonymization and pseudonymization, which are techniques to use in privacy. And I'll just give their overview of what it is, and I'm going to show a very cool example from my time at Utdanningsdirektoratet, the Directorate of Education and Learning, where we had to give out aggregated statistics with different levels and how hard it actually was to anonymize it. Then we can move on to encryption and keys, and there we're just going to go through like symmetric keys, asymmetric keys, and key exchanges, right? The foundations of how the internet works. We'll just go through them so we all remember how they are and how they work, and how we can communicate securely and store data securely, right? And at the end, practical insights and tools, just some cool things that I've done, like how to encrypt and version control your secrets and get them deployed. We'll look into like managed identity on Azure as an example of giving your app an identity, and we'll look a little bit into always encrypted on SQL Server, which is kind of a client encryption technique. So some more practical stuff, but things I've used in real life, and I think it's super cool and kind of want to show you. So in this kind of part 1, your brain, I will show some text because the legal text is not a lot, but I know your brains would read the text on the slide first, right? And then I'll try not to start talking about something else while you're still processing, but I'm aware that in some slides there will be a bit of text, but not more than kind of this, so don't worry. You were probably expecting like a huge wall of text. So I just always like to start with this. Like if you write down kind of your mother's name on a to-do note at home, this is kind of not the legal stuff we're talking about. We're going to be talking about kind of law and compliance and rules we have to follow and things we have to do as developers based kind of from a organizational standpoint, like from a business standpoint, thinking about our customers, but also our employees. Remember that the employees are just as well protected by laws as customers. But first, let's kind of think about what is personal data. So this is a very wide definition of what personal data is. Like you have the obvious ones, right? Name, phone. The ones that are not as obvious, IP address, right? And the reason it's personal data is because somewhere at the ISP, they are able to connect that IP to a individual, right? Natural person at a certain date at a certain time. So that makes it personal data. Things you don't think about, like an audio recording. An audio recording where you can recognize someone by their voice, that means that recording is personal data. And then we have another layer, right, of more sensitive data like race, ethnicity, politic views, religion, and health. These are considered more sensitive. And also personal data about children. They're also considered sensitive, so you have to do even more when you're talking about that kind of data. And in the EEA, like the EU, I might say EEA European Economic Area, or EU, but I'm talking about the same thing. We have very strong laws, right? They're kind of like, we have by law the right to the protection of our personal data. And as individuals, this is amazing, right? We are so well protected. And we have all these rules about lawfulness, fairness, transparency, and businesses using our data, our personal data, need to like have specified, explicit, and legitimate purposes to actually do so. And you cannot use that data for anything else once you collected it. So the EU laws for this are super strict, which is good for us as individuals and a pain for us as developers and working on products, right? And you have like different ways of giving. You have consent, I'll get back to that, but you have also like legal interests, which is how Meta says they're gonna use your data for AI training, like it's in their legal interest to do so, which is, let's see how that turns out. And then, but you also have contractual obligation, right? So if you sign up for my service and I'm using Stripe as a payment provider, then I, of course, have to let you know in my privacy policy that I'm using Stripe, but I can put your personal data in Stripe because I need to do that to do what you asked me to do contractually. So that's what kind of contractual obligations means. So yeah, here's a lot of points, and this is kind of the demands that the GDPR puts on us as developer and corporations when we're working with personal data for individuals in the EU. Doesn't matter if you're a US company. If you're working with the personal data of an EU citizen, you have to comply with these laws. So that's a bit weird, right? Because, yeah, these are laws in the EU, but how is it with international transfers? So we have good privacy laws inside the EEA, and that's kind of okay, but how can we transfer personal data to countries outside the EEA? And I'm going to go through kind of the two basic ones, which are standard contractual clauses and adequacy decisions. And these are kind of the mechanism grounds for transferring data to third countries. There are a lot of other ones mentioned in the GDPR, binding corporate rules, code of conduct, blah, blah, blah. There are some exceptions, like if your life depends on it, it's possible to do it. But basically, these are the only two that is kind of, there's precedence on how to use them, and all the other ways are kind of, there's no precedence, so there's no practical way of using them. This is kind of the biggest slide I have in text, this and the next one. But summarized, when you have an adequacy decision, it means that the EU Commission has decided that this country has the same level of protection as inside the EEA. So you can transfer data there. You don't need to do anything special. You still need like a data protection agreement and all the stuff that you need inside the EEA as well. But they're kind of stamped this country as approved. Examples are South Korea, Switzerland, Japan, and the US. But a bit on and off on that one, and I'll get back to that. The other one is the standard contractual clauses, the SCC. It's kind of a pre-approved contract that the EU Commission has made. And it has been updated and includes kind of cloud and data protection agreement. But the important thing with this one is that you, as the data exporter, you are responsible to make sure that the data importer, who might be in the US, you're using a US SaaS service, right? You are responsible that the US laws are adequate for protecting the personal data you are sending there. So while we didn't have an adequacy decision with the US, kind of you were the one who had to say, okay, the EU Commission couldn't approve the country. How are you going to do it, right? So, but this is a way of transferring personal data as well. World's quickest timeline, because it does matter a bit when we're going to talk about these adequacy decisions and using services in another country. So in 1995, we got a directive in the EU and the EEA about how we're going to process personal data. This is a directive, so it means all membership countries in the EU has to apply it in law for themselves. So in 2000, 5 years later, that was actually applied as law in Norway. And at the same time, we got an adequacy decision called Safe Harbor. I bet these names will sound familiar for a lot of developers at least. And that was kind of the decision that the US, you can transfer personal data there, that it's as well protected there as in the EEA. Then Schrems 1 came 15 years later, because a lot happened during that time, right? From the 2000, we got the iPhone and the cloud took off, right? And the 3 big ones in cloud, they're all US based. And Facebook came, social media, right? It became much more, much bigger. So Maximilian Schrems is quite famous. He's an activist now, but with a legal background, and he took on Facebook, and it validated the whole adequacy decision with the US. But only 10 months later, they just created the Safe Harbor 2.0, which they called Privacy Shield. And in 2016 is also when GDPR came. It was those 2 years until 2018 when the GDPR came into effect. I think the only thing I was working on was becoming compliant, and I think that goes for almost everyone working in IT in the EU at that time. Definitely everyone touched it somehow. But of course, most people know in 2020, Schrems 2 invalidated Privacy Shield because it was kind of the same shit, different wrapping. And yeah, we were 3 years without an adequacy decision before the new one came last year in June called DPF, which kind of, yeah, we'll get a bit back to it, but we have adequacy decision now, so now you can use Google Analytics and you can put things in US data centers, but feels a bit fragile, right? So there are 2 laws that kind of all the Schrems judgments were based on. And I think the bottom one, the executive order, it was Ronald Reagan who made this one in like, I don't know, the 80s. But it has to do with bulk surveillance at the border, right, and storing data and things that are not compliant with the GDPR. And these are the laws that kind of killed the Privacy Shield. And yeah, they were cautioned about this before they made the adequacy decisions. And these haven't been removed. They are still there. But we got a new executive order from the Biden, from Biden, and it kind of adds some more. Yeah, be sure you have to save all that bulk data before you do it, and a bit new ways for us to complain, right? But the laws are still there, and we should maybe be prepared for a Schrems 3, the trilogy. So at the time when Schrems 2 was active, I was working in a startup, health tech startup called Confrere, and we were doing a web RTC and end-to-end encrypted video calls between doctors and patients. And we were going into Germany, which has even harder privacy laws, like on top of the GDPR, especially in healthcare. And yeah, we had to do so much stuff here to become compliant, because when Schrems 2 happened, we were using AWS, we were using Twilio for SMS and emails. So we had to start going through how we could be compliant with German healthcare and the demands there. So we had to just switch Twilio to our Swedish SMS provider, because even though you're using a GDPR compliant service, does not make you GDPR compliant. So a lot of like services you use for analytics and for SaaS providers, platform providers, they say we are GDPR compliant. But that doesn't mean you can start using them and think you are GDPR compliant as well. It means that you can be GDPR compliant using them, but all the responsibility is on you. Maybe you have to encrypt, maybe you actually can't use the service, but they are kind of doing everything they can on their side. And as long as you follow the rules, they can too. But it's to put all the responsibility on you. So we, for example, we had problems with the integration with these SaaS providers, CDN exit nodes, like weird stuff, and I'll get back to that. But like the first thing we had to start thinking about was like data center location, right? And we were on AWS. I just took like this Norway as an example, because that's probably the most used one now by Norwegian companies from that period. So we had to kind of prove that we were operating in the EU, in EU data centers. But there were still issues with like, there's still American access, right? And support and updates, and the company, Microsoft, is still under US law. But we were on AWS, and they go out and they say, like, we have to do risk assessment, right? What is the risk of the US intelligence coming and taking our data? And AWS says we haven't got a single request for data. That's probably because they don't have like G Suite, Google Workspace, and Microsoft 365, right? They'll go for your emails, not your database. And of course, they are not allowed to tell you most of the time, I would assume, anyway. But all cloud providers say they will object and inform you if this happens. And it came some precedents, right? There was one, you don't have to read all this, but as I said, I know you're going to do it. But I underlined, like, it was a ruling that said about CDN and cookie handling, and they said, like, doesn't matter if you use a European data center, because if the American company has access, it's not good enough. So yeah, hard time to navigate. And yeah, it was also about CDN exit nodes. So they were actually testing, like, the Portuguese National Statistic Institute, they got a 12-hour warning, stop using the Cloudflare CDN, because we are seeing us hitting US exit nodes or nodes in the CDN network. And we were trying to do this because we were on AWS and CloudFront, and we had to make sure that when anyone was certifying us in Germany, they would always hit the EU CDN node, right? Even for our static web apps and stuff. It was crazy. And another health startup called Doctolib, they were challenged by professional associations and unions for using AWS, even though they were in French data centers, because they had a platform used to book COVID-19 vaccinations. But they were allowed to do so because they had legal safeguards in place with AWS, like good contracts, risk assessments, but they also did client-side encryption. So the data was protected by encryption. And it said when you had a reservation and appointment, but it was encrypted and no health data. So end-to-end encryption. And we thought, like, yeah, this is a great idea. They use a tool called Tanker.io, which has a SDK and a key management solution for the client side. And then Doctolib actually bought that company. That's how valuable it was in healthcare at that time to actually get around these problems. So we didn't get to try it, only read the docs and realized that it was out of reach. And of course, most people remember that Google Analytics was actually made, decided to be in violation of the GDPR. Even if you turn off the IP tracking, right, you cannot hit a web server without saying who you are, saying your IP, right? So when you hit the server, your personal data hits the server, and then, yeah, Google Analytics doesn't store the data, but your IP, the IP of the user in the site, right, has hit the edge servers here. So it was a lot of things around this. But now, of course, we have a new adequacy decision, as I said in my timeline. So now it's okay. But just be aware of what I told you. These laws are still in effect, right? And there's still a chance that this adequacy decision might just disappear. And then suddenly you have to take all these considerations again. So I think we as developers, like, I've gone through a bit like the laws and rules, but also this with the international transfers. Like, we choose often the data centers, we choose the providers, we choose what kind of data store to use, what kind of security to use, where we transfer it, policies, right? And we have to think of all this, data minimization, auditing, retention, and we'll get back to encryption, right? So it's important to kind of know a bit the history here, know the laws, know the issues that can arise. So when we do kind of bigger decisions around our solutions, we are aware that this is something that can hit us and can hit the business, right? This isn't just about the, like, small things in our code and that is, this is annoying as a developer. We work for an organization trying to achieve something, like, with a goal, so we need to be part of this and have this top of mind. These are considerations we have to do when kind of doing system design and working on products, right? It's our responsibility. So I'm sorry to say the fun part is over now with all the laws and legal compliance and text, but it kind of put the groundwork for everything, right? The foundation for everything. And before GDPR, for people who worked with personal data at that time, you know it was a lot more slack than it is now, and that this is a very big improvement for individuals living in the EU. Okay. Anonymization and pseudonymization. I see a lot of privacy policies. I'm actually kind of one of those people that read the privacy policy before I sign up. You could maybe have guessed from the first part. But I often read this. We may anonymize your personal information so that you can be blah, 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 blah. It doesn't matter what I read after that, because I'm always skeptical, because it's so hard to anonymize data. And most people really underestimate how hard it is. So the definition of anonymization is the process of removing personal identifiable information, as it says here. That means it's impossible to reverse engineer it. That's the definition of anonymization. If you can reverse engineer it and get back to who this person was, it's not anonymous. There's no wiggle room there. An example is, for example, when I work at Utdanningsdirektoratet, the Directorate of Education and Learning in Norway, we had aggregated test score results from school. And for example, if there was only one student in that school, then the average test score would be that individual's test score, right? These are children also, so we needed to hide that. And I'll show you that example after, because it's a lot of fun. Encryption is a safety measure, so and anonymization is a privacy measure. It means encrypting something doesn't make it not personal data, because it means it can be restored. That includes one-way hashing also, and because you can later hash and then match the hash, right? So it's possible to figure out who this was. And yeah, if it can be restored, it's pseudonymized. And that's kind of what we do when we want to hide personal data, but we need to be able to identify someone, right? So think database identifier in your users table, right? The ID. But pseudonymization, as I said, it can be restored. It can be restored, but you can use data somewhere, and it doesn't matter where it is, right? If you have an ID in your system, and there's like a secret database in an offline server in your headquarters, and that's the only way to identify the user using that hash, is still personal data. That's how strict it is. Global kind of, doesn't matter if it's inside the EU or anything, it's kind of the definition. And so it doesn't have to be publicly available for you to be able to re-identify. So this is the example I gave, the user database identifier, personal information, because it can identify someone. And I always, when I try to be hard with people, I always I call it the library computer test, right? If you had a URL like this in your web app and someone visited from a public computer, it gets saved in the browser log. Remember, this is personal data, right? So if the user kind of chose to do that, then it's okay, kind of. But we have to be aware of this even when making URLs and endpoints, because, yeah, you have to be aware. Maybe you need some kind of check or something. A lot of people have that, like I'm on a public computer, right? Because they're thinking of these scenarios. And also machine-to-machine, if this was a machine-to-machine call for some APIs, we have logs everywhere. And that might be fine, legal obligations, right? You need it for debugging and so on. But make sure you have like time to live, all these things, and that you are actually aware of where you send personal data. So yeah, pseudonymization is a tool for protecting personal data and a tool to reduce risk. That we are, by law and by the GDPR, we have to use it as a tool. If you could use pseudonymized data instead of the real personal data, then you have to do it. Because if not, you are not minimizing and protecting it good enough. So I wanted to go into, as I said, from the Norwegian Directorate of Education and Learning, a bit about anonymizing statistical data, because that was one of the most fun things I worked with inside of this domain. And every 4 years in Norway, we have an election. And at this time, when I was working there, we went from a red government to a blue government. And they wanted to, we are not going to have aggregates just on municipalities anymore. We're going to go down on school level for national tests to have public data on how schools are. And yeah, so we had to add lower aggregates, and we had to use proper anonymization because these were kids' test results, right? So I just going to go through it because it's a bit cool. This is very simplified. Like it was many accesses on the data set, but you get the basic idea of a problem. So we had like an aggregate for boys on a school, and for girls, and then we had an everyone aggregate, which was kind of the sum of those two. But as I said earlier, if we had one student in one of these aggregates, we had to suppress it. It's called primary suppression. This one has to be hidden because it's the actual test result of this student. But if there are some mathematics nerds in the room, you maybe realize that if you just take the everyone aggregate and remove the girls, then you actually have the boys aggregate. So we needed to do what is called second suppression. And at this point, we're actually losing statistical data just to preserve anonymity, right? The everyone by itself couldn't identify a score if the girls' pool was big enough. But it wasn't as easy as just doing this per school because we had higher aggregates, right? So this is a terrible slide, I'm sorry, but you can see the different levels on the left side, and the one with the arrow, we have the school we just suppressed in, but if we take the municipality and we remove the other school, because in this example, it could be 1,000 school, but if it was just one unknown, then we could solve it from there, right? Because we have a higher aggregate. So we need to second suppress that school as well. But of course, it's aggregates down on that school. So just as we suppressed only 2 aggregates on the other school, we need to go down in the second suppressed school, down 1 level. And it makes sense to maybe second suppress on that school the everyone aggregate. And here we have high numbers, so we're losing data here just to hide that data from that other school, because we don't want people to be able to solve it and get that individual student's test score. And a good rule when doing suppression is like, let's take the smallest one, right? Hide the least amount of data. But if you were a bit observant, we did a mistake here, right? Because we were not considering the higher aggregate. So the municipality aggregate, as you can see here, the everyone has 2 unknowns because it's suppressed in both schools, but we suppressed the girls in the second school, so there is only 1 unknown on the boys' axis. So we should have done like this. And yeah, some weird things, like we have Svalbard in Norway, which is like a little island, and if we only looked at one axis, like 1 girl on the 5th level of school there, then it could go up, right, all the way up here, and it could go, we'd have to choose something. The one on the right has fewer municipalities, but that's Oslo, so it has a shit tons of schools, so we have some rules, right, to go down and blah, blah, blah. They actually put Svalbard under Finnmark, another county in Norway, to avoid this problem, because it would always be the one that would be second suppressed, so because it's the least amount of students there. But yeah, crazy. And we had so many axes here. We had shit tons of axes. We also have private and public schools, so you could use kind of a second axis to solve over to the problem we're looking at now, and we divided them into level based on their test scores. It was an average per level. So this was the funniest problem I think I've ever worked on. I worked together with the statistical department, and we solved this all in F# with like an algorithm that we had a test that was always trying to solve, that we made to try and solve all the statistical data. We used it on previous years. I think we solved it. So, but we used it on kind of our new algorithm, and we found it to be proofed. But we needed to always work on trying to hide as little data as possible, because it's easy to hide a lot, but it was really hard to go down and kind of show as much as possible without exposing personal data, right? And yeah, I remember I was dreaming about this suppression stuff. So I was talking with the guys in statistics, and I came one day and we were in a whiteboard in the meeting room, and I said like, now it's getting too far. I'm dreaming about this. And he was like, finally, you're one of us. So that was fun. So back to that privacy policy. Last slide on this part, but yeah, now you kind of know where I'm coming from. When someone says they're going to anonymize my data in some kind of pool, I'm not too sure they're actually doing it. Always a bit skeptical, because anonymization is hard. So that was fun. I just think it's a fun example of a real-life problem where anonymization is very hard. But now to the fun part. Encryption, I'm saying that about everything. Encryption and security. And I just want to drag us through like how the internet works, right? And this is like, people have read about this, people have had it in school, but it's kind of easy to forget, and it's kind of fun to recap everything. So you know these two, you've heard about them, I'm sure. And you most likely heard about these two as well. Eve, which is for eavesdropper, and Mallory for malicious. But luckily we have encryption, right? If we met in real life and we had a lock and we had 2 keys to that lock, we could take 1 key with us and one each, and I would be able to send things across. This is what we call a symmetric key, right? We have the same key on both sides, and it can both lock and unlock the lock. And for the example of all this, like, you can't pick this lock, not with today's technology, right? Unless you have a quantum lock pick, but we'll get back to that. So both can encrypt and decrypt, right? So that's a symmetric key, but we had to meet to make this work, right? To get the same key. We had to somehow come together and make sure nobody was looking, and I could look, if I was Alice, I could look Bob in the eye and say, like, let me have your key. And then we kind of know that this is a safe way to communicate. But what if we were unable to physically meet to exchange keys, right? And for that, we have what everyone knows as the Diffie-Hellman key exchange. And this is in practical use today. Like, we know it with kind of prime numbers and stuff, and now it uses like elliptical curves. But these kind of basic things are the foundation of everything. And yeah, they are always been made more secure, but the basics here is still how it works. So it's good to know. And it's a very easy way to explain the Diffie-Hellman key exchange. First, you start on agreeing. I like to explain it in colors, right? But the assumption here also is like you cannot divide a color into the 2 colors you use to mix it, just as the lock cannot be lock-picked. But it's a good explanation, so bear with me. And this common color we agree on, we share it with each other through our public channel. It doesn't matter if the eavesdropper hears about this color, right? And then we pick for ourselves a secret color, a secret key, a secret color that only we know, and we're not going to share that with anyone. We then mix those 2 together. So Alice mixes her private key with the shared color, and Bob does the same. And what we do, and again, the point here is very important, that you cannot take that color and use some kind of tool to find the 2 colors used to mix it. You cannot sit in a room and brute force it, because with today's technology, it's impossible, for the sake of the example, right? If it was colors, you could, of course, be at home mixing color until you got a common color, maybe in the end find the 2 colors. But for this example, that's impossible, because with today's technology, you can't do that. We then share the mixed color. So note that we're not exposing our private key. We're mixing the mixed color from our secret key with the common color. And then we add our own private key to the other person's mixed color. And we arrive at a shared secret color. So if you kind of reverse engineer this, you'll see that the nudient on top equals the 4th color on the top row. It equals the shared color and the secret key of Bob plus our secret key. And if you go the other one, it would be the same. So basically, we get this. That's why it works. But we managed to do it without even exposing our private key. And this shared color we arrived to is this kind of symmetrical key that we talked in the start. So we shared keys without ever meeting. We're back again here. And yeah, symmetric keys uses the same for encryption and decryption. It's much faster. It's the fastest way of encrypting and decrypting and talking back and forth. It doesn't demand so much computational power, right? It's fast because it's less complex math than some of the things we're going to get to. But they were all of them deceived. for another key was made. So yeah, we haven't solved the problem we talked about earlier, right? We didn't meet, so we don't know that we actually talked to Bob. It could have been Eve here saying like, yeah, I'm Bob, let's exchange keys. And on the other side, yeah, I'm Alice, let's exchange keys. And just decrypting and encrypting it again and passing it on. And you would never know that the eavesdropper is here in the middle listening in. So this is a classic man-in-the-middle attack. And here at the kind of key exchange level is where it could happen. This is today's sad news for some. We need to trust someone. The whole internet is built on trust, keys and certificates. But we need to learn about asymmetric keys for this. Asymmetric keys is kind of, we all know this as developer. If you never touched asymmetric keys, even though if you didn't know their name, as a developer, that means you maybe never used GitHub, and then I'm starting to doubt you know what you're saying. Like, we know this. Public keys, the public key, we mostly use SSH keys, and they are for authentication, but there's also like GPG and PGP, which is the same implementation, but it consists of this key pair, where we have a public key for encrypting and verifying signatures made by the private key, and only the private key belonging to that public key can decrypt the data and create the signatures that the public key can verify. So in this case, both Alice and Bob has a key pair. The one on the inside here is their public key, which you can share freely. It's you don't have to keep it safe, but your private key, never show it to anyone, right? So we can swap these now. We don't have to do the whole key exchange. But at this point, we haven't solved what we talked about earlier, right? We don't know that we actually got Bob's public key. And this is where trust comes in. You need someone you both trust to be able to trust that public key. And kind of GPG keys, they try to solve this with kind of the web of trust. So let's say I met someone here in real life, we exchanged keys, then I could use my private key to sign their public key. And that means if you trust me, you can trust them because I signed their key. But it's way too complicated. But that's what we call it kind of. Then I could publish it on a key server for GPG, but we kind of all trust GitHub, right? So I could put my SSH key there and my GPG key and sign my commits. And since we trust GitHub, we would trust that, yeah, the GPG that is connected to my profile is actually me signing the commits. Keybase, for those who use that, was kind of a way to sign across social media to confirm which accounts you had by signing them. And you could know that if I could be 100% sure if I knew that was you on Facebook, I could go through there and know that's you on Twitter, that's you on GitHub or other social media, right? You have SigStore, which is for artifacts we create and signature. SigStore, I would recommend going and reading about SigStore because they have so much good documentation about how to do safe packaging and signing of packaging that goes way beyond what we are mostly used to, like a MD5 hash, right next to the zip file or whatever you're downloading, so you could verify it locally, but you never have. And of course, the last one, the certificate authorities for these TLS SSL certificates. And that's the big one at the end. Like that puts the whole internet builds on trust on the certificate authorities. And our browsers and operating systems are pre-programmed on certificate authorities to trust. So for example, here is a certificate authority at the top, a web server, and this is like the most simplified TLS secure handshake from a browser. It's a bit more about like which protocol to use, cipher suites, compatibility and stuff, but we're going to show it's the kind of same basic we've been going through, right? So the certificate authority has some kind of, they approve that, yeah, you are this business on this domain. And they sign a certificate for you and give you a public and private key for that certificate. So when Alice comes from her browser and tries to talk to the web server sends the certificate signed by the CA, and which contains the public key, but they also sign it using the private key they got. So with the signature, Alice knows that, yeah, the web server that sent me the certificate, they have the private key, because if not, they could not sign it. And the browser trusts the signature also of the CA on the certificate. So this is simplified. It's a big chain of trust up, but this is basically how it works, simplified. So Alice just creates some key pair on the fly. She verifies through the whole key exchange procedure that is still the same public and private key that is on the certificates, but the web server doesn't care who Alice is, but to exchange a symmetric key and start communicating fastly and securely, we do the same. We're back now to starting this Diffie-Hellman key exchange, right? But we have verified the keys of the web server. And you could do the same with people. So that's basically how the internet works. Asymmetric keys, symmetric keys, and these kind of handshakes, signatures. And as developers, we mostly know or use JSON Web Tokens in a lot that we do. And this includes all these kind of things, right? It consists of 3 parts, the header, the payload, and a signature. So the header just is data about how it's encrypted and stuff. But the signature is signed by the public certificate of the issuer, right? So the issuer is either in the token itself, or you usually, in your middleware, you point it at an authority server, right? Maybe Microsoft AD, for example, or Microsoft Entra ID. Sorry, Microsoft. And we send it right in the header, and we verify it. And since we have the trust of the internet, right, we can go over HTTPS to this well-known endpoint that we use for OAuth and for JWT. And there, the public keys for the token are hosted. So we can just, when we start our application, we could fetch the public keys and say that as long as we verify that the token coming in is signed by the private key owned by this public, as long as the token is signed by the private key belonging to the public key at our trusted issuer, then the claims in this JWT tokens are true. So here we're using kind of asymmetric keys, and we're using the trust of the internet and certificates to actually get the public keys we're going to verify against. And JWTs are what we call stateless tokens. Might not make sense to you because it is a lot of state in a JWT token, but it doesn't have any state on the server, right? It comes in and it's kind of self-contained, so we just verify the signature and then it's like, yeah, it looks good to me. While, because it's signed by the issuer. And that can reduce a lot of networks requests because we already have the public key, we got it, and we are just verifying on the fly. Stateful tokens are just arbitrary strings, like they don't mean anything because they're stateful. They come to the server. It's just a bearer token in your header. And then when you come server side, you actually have to go to the authority server and ask, hey, I got this token, is it valid? And it's like, yeah, it's valid. And then you have to go fetch like, yeah, but who is it? And then you get kind of the ID token. So it's a lot more network effect. If you have a SPA or something, you can always cache for a short amount of time to avoid that. We did this. I was at If Skadeforsikring, insurance company here in Norway. And we use opaque tokens because it has some plus. Because if the private key gets compromised or lost, then they can sign their own JWTs. And with opaque tokens, if a user, for example, clicks log out on one device, you can actually just right away invalidate the token, and all requests will start failing on all their other devices because the token they're sending is invalid. While if you're using JWTs, it might get a bit more complicated because they have valid tokens that are signed. So keep short time to live on JWT tokens, so they'll have to be renewed. Then you don't have to have like, yeah, I don't know, web sockets into every open browser the user have to actually log them out, and can get complicated. So it has some pluses, right? And I promised to tell you about the biggest attack vector of all, quantum computing. It basically breaks asymmetric keys, which is kind of built on, as I said, we all know, large prime numbers, or now it's elliptic curve problems. So yeah, quantum computing will come, and Shor's algorithm will manage to solve, kind of, if you have the public key, you can solve the private key. And we need to also think that everything we store now, or an attacker stores now, can be decrypted later. And it's in very small text down there, but if you search for Google's post-quantum cryptography blog post, it's a really good, cool blog post about the future, new algorithms coming, and also like things that, like businesses that are very that can be attacked like this, how they can already start now to be a bit more quantum computing resistant, and how they can start planning a transition. But most of all, it's just a very fun read, right? So there's a lot of things to consider, right? Private keys can get compromised, stolen. What do you do then? Someone can sign with your name, basically. You saw this often with having a master key, and the key you use, the sub key that is signed that master key. If you want to go into this, it's crazy how much you can do. You can have a YubiKey. A lot of people use that. A YubiKey basically does all the signing and stuff on the hardware device, and the private key lives on the YubiKey and never leaves the YubiKey. That's why it's considered so safe, right? Because everything cryptographic happens there in that secure enclave or whatever you want to call it on the hardware. SigStore, check it out for artifacts and signatures, and their documentation is amazing to explain kind of all the problems with having long-lasting private public keys, asymmetric keys. And they really get into this last part, right? If you had a package used by millions of people and someone gets your signing key and they can re-upload something and sign it with that key and replace something that people use and it has the same signature, right, safety-wise. They go into a lot how you can get around that. So great. We went through the 3 things that keeps the internet together, right? We can exchange keys, asymmetric keys, and sign and encrypt and decrypt and verify signatures thanks to trusted third parties. We know how a symmetric key can be decided without every meeting, and using that symmetric key, we can actually fast and cheaply, computational-wise, communicate. So that's a lot, but like I think these 3 is so important to be reminded of how this works. We touch this every day without knowing it. We touch it when we open our phone and go to a web page, right? All this happens behind the scenes. So the last part is just some cool different stuff that I've done in different places that touch a bit on this with encryption and especially in keys. And the first thing, like people would probably know this, like you start a new project and to onboard a new dev, they kind of, I need to send you the .env file with some secrets that give access to different integrations or, yeah. So we need to make kind of it easy for ourselves. I am a big, I love putting secrets in source control on GitHub, why not? And so I want to just quickly introduce you to SOPs, S-O-P-S. I think it came out of Mozilla, I don't really remember, but it's a great way of kind of using keys to encrypt files that you have in your Git repository. And it has a lot of things that you can use. For example, Azure Key Vault, which I'll show you. I simply just make a sops.yaml file in my root folder to tell which key vault I'm using. So I have to, of course, log in with the Azure CLI, and someone needs to add me a group to give me access to this key vault. But then I can start actually decrypting and encrypting files in the repo. And SOPs, it gives you this crazy JSON or YAML or whatever. But as you can see here, it's just the top row is just data, and then it is a bit info about Azure Key Vault. And it tells which key in Azure Key Vault to use for encrypting the encrypted key further down. Because this is asymmetric and symmetric key. So our data is encrypted with a symmetric key, so we can keep encrypting and decrypting very fast. And then that symmetric key is encrypted by the key that is in Azure Key Vault. But everyone has access to that if they actually, if they can reach Azure Key Vault. So basically, you control access to encrypting, decrypting secrets in the repo, the same way you kind of would manage it for access to email, right, in your Azure AD. Very quickly in a GitOps flow. For example, here, this is a Git Kubernetes secret with some secret data. I make a SOPs file in the repository. Here I'm using a PGP key that I have on my computer to encrypt the data. And here you can see that SOPs also can, you see it still contains some of the, it's still valid YAML for a Kubernetes secret. And the cool thing is I'm going to go a bit too fast through this, but I can actually put key in the Kubernetes cluster, right? If I'm using Flux CD, for example, or using Argo, it supports this as well. So I give the cluster the secret key as well, and then it's able actually when I commit encrypted stuff to or secrets to the repo, and it pulls it and starts deploying it, it can actually decrypt it inside of the cluster. So we have a safe way of giving and making sure these secrets actually exist on the can be applied on the cluster, right, and exist there. So I also want to show you managed identity in Azure. It's actually something you can just turn on a web app, for example, and it gives the app an identity, kind of a user, think of that. And you can also turn it off. Of course, you should use infrastructure as code. And it basically just opens kind of an endpoint that the app can call locally, and it gets kind of a username and password, a client ID, client secret, to a token to communicate with. And then you can use that. You just use this default Azure credential, which I'm sure most people have used. But most people don't know that behind the default Azure credentials is a lot of different, and you can pick and choose from this one. But one of the first ones is checked is the managed identity credential. So it actually, before it starts looking if you have Azure CLI installed or you're using the Visual Studio Code, it checks for this endpoint. Hey, can you give me a token? And it says yes, because it's kind of in the secure zone running in Azure. And then you can start calling like app configuration, where you can have kind of think of this as the .env file, right? Now I can just use that default Azure credential, and it doesn't matter if you're the app or a developer. You can go here and you can get kind of the secrets you need to get started. And here's even some references to Key Vault and secrets. And yeah. So in the web apps configuration itself, it's no secrets, not even in the connection string. Connection string just says where to find the database. And then you can kind of get this token, and we can even put it on the connection, and it can connect to the database with this managed identity. So the best way to handle kind of keys and tokens is not to handle them at all. Managed identity lets you do that. So the developer experience becomes just AZ login. A new developer on your team, you add them to the developers group or your team's group. They run AZ login, and they can start up the app. They get all the secrets to call like integrations and stuff. And then maybe for the writing stuff, you run up some Docker containers, but you can get someone started very fast without having to share anything. Yeah, and I've done this a few places. I went a bit fast now, but this is kind of you can't, for people thinking about this, like, yeah, no, you can't program on the plane now, right? Because you need actually to get the secrets from over, you can't run things up locally. But for the places I've used this, like, okay, then I'll save some work that I can do on a plane. I'm not going to design my whole developer experience, security, and kind of application around that we should be able to program on a plane. Some, like without internet. Some cases, it might be worth it, but yeah. It's a cool thing to check out. But it just works kind of in the Azure way, but in the Azure scope. But there is a lot of alternatives on other platforms for giving your app an identity. The last thing on this part I'm going to show you is a bit about always encrypted, which is a feature of SQL Server, but almost all databases have some version of this. And we actually use this. This is great for data confidentiality. We used it. I was at the Directorate of Health. I've been at a lot of directorates, I realize now. But here we were getting health data in messages coming from joining systems, but we're not allowed to see that data even as developers working in the database, right, in production environment. We shouldn't be able to just open the table and see health data about individuals in Norway. It was no reason for us to do that. And if there was a reason, we should ask someone who actually had a reason to go there, someone on the business side working with the data, and ask, hey, we actually have a valid reason to do it, right? So this is a great feature. We kind of, it lets you do this thing. I talked about Doctolib earlier, and they bought this company Tanker, and they were encrypting things client side. So what you can do here is actually, you just set a column in your database to be always encrypted, and if you have the key, it will kind of get that row, decrypt it on the client side inside kind of the SDK, and you won't even notice that it's getting encrypted and decrypted on the fly on your client side, but the database engine never sees that data in plain text. And you kind of had, it works the same way. You have kind of a column master key, which is a key value pair that you have the secret key to on your client, and it's encrypts a symmetric key that is stored on encrypted on the server. So everyone who has the master key can get that symmetric key to their client, decrypt it, and start decrypting and encrypting data. And your app, it can have, for example, a managed identity, right? And you can add in Key Vault that this managed identity should be allowed to get this private key. So then your app, who of course needs to be at least able to encrypt data, but in most cases, your app needs to process the data as well, but only, for example, in the production environment. So then you would give it a right to get the key, for example, from Key Vault. And you don't need to like install the key right locally, because you can also be given access to Key Vault. So maybe you could have, you can be pinned, like be allowed to access the key for 1 hour if you actually needed to work on some data. So there's a lot of cool things you can do here. And this brings us also in kind of the secure computing space. Because if it's not plain text, but only ciphertext, it's kind of hard to work with the data in the database to do queries and stuff. Things need to happen on the client side. But it is possible with this kind of secure enclaves. And this is kind of in the CPU, right? This secure enclaves. It's called like trusted execution environments. And Intel and AMD, and they all have it. And it also works with trust. But the simplest way to explain it is not really how it works, but it's so similar. Think of it as your CPU basically reserves a bit of memory. It has some secure instruction. It secures a bit of memory inside the CPU, inside your computer and everything. It creates a secret key, and then you kind of get a public key that gets verified in Azure. So when you send a request here, it can do some more. It can actually decrypt the data. It goes to Key Vault. It's allowed to get the private key, to get the symmetric key, and can decrypt the data, work on it in here, and then make sure it's encrypted when it leaves out again. So there's no way, kind of, the idea is there's no way to get inside this secure enclave in the CPU once it's made for this perfect. So this is what we call kind of, you have data in transit, right, which we see in the middle. We have data at rest, which kind of the data encrypted in the database engine, and this we call data in use. So we're securing it in use in the memory or in the CPU. So yeah, I went through a lot there at the last one. It was mainly meant to just kind of inspire you to look into it. So we looked into a lot of stuff, right? The first one was that everything is personal data, right? Everything about encryption, portability, and third-party providers, and how much we actually have to think of as professionals. We talked a bit about anonymization and pseudonymization. I showed you how hard it can be to anonymize data, right? So we should know what we're saying when we say we're going to anonymize. And yeah, the business side often is very lean on that, so I like to arrest them, but that's not anonymized. Like, that's how you get popular in your business. We looked at encryption and keys, which we kind of all knew from before, but now we know it a bit better. And we know that the internet still works that way. And we touch this every day with our SSH keys and when we sign stuff. And I showed you at the end SOPs for encrypting secrets and being able to share secrets inside your team or your company for that matter, and still have the kind of same access control that we have for other things like email and the same kind of governance. And then we looked at always encrypted. No, managed identity we looked at, which I really recommend you look into if you're using Azure. It can also be a sidecar in your AKS cluster, right? So you can still use managed identity for Kubernetes apps living inside of a Kubernetes cluster. And there are the same concepts exists in the other cloud services. And yeah, the database, secure enclaves, and yeah, that's also a whole nother topic. And then, of course, the main point, none of this matters because of quantum computing. But luckily, that's a bit ahead of us. Just to end on a funny note, I wanted to show you this one. This is a very funny Twitter post I saw about a landlord who were giving out free fruit to the tenants. And then suddenly came like a notice from the landlord. I've been filming you and analyzing which fruits you take. And in the bottom is like Devon, 56 blueberries, etc. And it's like kind of shocking. And then the disclaimer at the bottom is the best. I use the data to know which berries to buy. It's fine for me to do this. If you live in my building, I can use your data. Thank you so much.